So our first axiom was regarding preparations. So I didn't have that word in there last time. It's a further specification. I think I covered most of the remarks I wanted to. I'll give you examples of Hilbert spaces. And now we'll turn on to measurement. So I'm skipping the transformation box I drew yesterday, and we're going right to measurement.
Joe?
Yeah.
What do you mean in this context by rank 1?
Oh, I guess I didn't define that, did I? Sure. So how many of you would like a brief review of projection operators, including description of rank? Okay, so very quickly, where's a good spot to draw this? All right, I'll just... A projector pi is an idempotent self-adjoint operator. Okay, so that means that self-adjointness is the condition that pi equals its adjoint. And rank 1, idempotent means that pi squared is equal to pi. So this is it's a linear operator acting on our Hilbert space. And it squares to itself. So basically, if you're familiar with subspaces of the Hilbert space, which I assume you are, so consider a three-dimensional Cartesian space, z, x, and y. The xy plane is a subspace of that three-dimensional vector space. If I have an operator that projects my three-dimensional vector onto that two-dimensional plane, so I just take essentially, I shine light from infinity down the z-axis and I get the shadow of the vector in the xy plane. That's a projection of the vector in three-dimensional space onto the two-dimensional plane. Similarly, I can project onto just the x-axis or y-axis or any axis, right? So then that projection picks out just one component of the vector. So if I have three-dimensional space, x, y, z, and I have some vector v, then a two-dimensional projection will project down into the xy plane. So this is a two-dimensional projection. So the operator that maps v to vxy, the map, so pi 2 takes v to vxy. And then we can have a one-dimensional projection. By the way, the use of a subscript here is I shouldn't call it a subscript. It's really bad. Here, let's call it this, a superscript. Would take v to, for example, these are examples. For example, takes v to vz, which is a scalar. So I can project here, and this gives me vz, which I guess is still a vector if I want to call it a vector. It's a one-dimensional vector. So that's what projections are. Now remember, Hilbert space is just a vector space. So all of these same operations apply, except we have complex vectors in a higher dimensional space. So a a rank K projector pi. So pi acts on our Hilbert space and takes us to some subspace V. Right? In general, we have this structure where V is a subspace of H. And then basically, okay. I'm going to say this, and I'm not 100% certain it's right, so you guys can correct me. So I think that a necessary and sufficient condition to characterize the rank of the projector is to talk about the dimension of the subspace it projects onto. So I'm going to say that the rank of pi is equal to the dimension of V. Is that right? I mean, it's certainly typically the case. Whether it's always the case, I don't know.
The dimension of the image.
It's the dimension of the image, that's right. Because the point is, if the vector has no support, no, not the vector, but yeah, well, V being the image of pi, I guess it's right. Yeah. So I think this is right. Certainly, you get the sense of it. There might be some subtlety about. There could be some subtlety here, but it's hard to imagine what that might be. But you guys get the you guys understand what's going on. Well, I'm just worried that, I mean, if suppose your vector is in the xy plane. And of course, I'm not talking about particular vectors here. I'm talking about the space itself, so it's probably irrelevant. My concern was this, and it's probably irrelevant. I mean, if your vector is in the xy plane and you project onto the zx plane, then you're just projecting essentially onto the x-axis. So certainly the image of that action is the zx plane, which is two-dimensional. But for that particular representative, if I project vxy onto the x plane, then I get just a vector constrained to one dimension. But I think that's irrelevant because it's just a particular instance.
Yeah, exactly.
Yeah.
You can make a change of basis there.
Yeah, so I think this is adequate. Okay, good. Good. So, but certainly you see the spirit of what's going on here. The rank of the projector is the dimension of the subspace it projects onto, which may or may not be encapsulated by this notation. But in words, that's correct. And so here it's important to note that where V is a subspace of H. So a subspace of a vector space inherits all of the properties of the original vector space, right? So V is itself a Hilbert space, but just of lower dimension. So projectors are very, very basic to everything we do. In fact, when you do a more kind of abstract formulation of quantum mechanics, it's all about projectors. The states are projectors, the measurements are projectors, so you really want to be comfortable with all of the kind of features of projections, because basically it's the central mathematical object for the way we're going to formulate quantum mechanics. So I was going to say axiom 2 is an ideal measurement procedure. Notice again, I'm referring to procedures. Our axioms are, for the moment, going to be essentially giving us a recipe for using quantum mechanics. An ideal measurement procedure is represented by a self-adjoint operator A so I should have said here, oh fine, I'll do it this way. A self-adjoint operator A with, okay, let me just stop there. A. Now I'll just point out part A of this is But I'm going to write this up here because we're going to discuss this a little bit. So 2 is not complete. 2a is that the set of possible outcomes. Now here, for outcome, I'm referring to pointer positions, right? So remember the drawing for the measurement box. There was some needle, and that needle, when you completed the measurement, when the light went off, the needle could point to one of several different values, which is your outcome. And we had K as our label of different outcomes. So I'm not referring to the state, but the actual quantity K that the label on the readout. The set of possible outcomes is given by the eigenvalues of A. And 2b I know what it is. Given preparation rho, given preparation rho, the probability of, this is just Born's rule, the probability of outcome K is Born's rule probability of K is equal to the trace of rho pi k, where A is equal to sum over L, we'll use K, sum over K, AK, pi k. Okay, so what I've written here is the spectral decomposition of A. Any self-adjoint operator admits a spectral decomposition with real eigenvalues, and pi are my projectors. Now, in general, the projectors in the spectral decomposition need not be rank 1. Does anyone know what familiar concept that refers to? Exactly. So if your measurement has degenerate eigenvalues, so if the operator has degenerate eigenvalues, then the projectors will project onto a subspace with rank equal to the level of degeneracy of that eigenvalue. So in our familiar three-dimensional example here, my measurement might be check if it's analogous. I mean, here this vector v represents a probability vector, and if I want to say what's the probability, well, how do I actually I don't know how to translate it into this. Okay, let me set that example aside because I don't know if it makes sense. But okay, so forget about the three-dimensional case. But anyways, this is familiar. This is what you know. So notice that let me tell you at least two things about this. The first is that we have two different empirical aspects of quantum mechanics. So in the early days, quantum mechanics was adopted by the community because of its structural predictions. So it predicted the spectroscopic structure of atoms. So that's associated with identifying sets of allowed eigenvalues of the energy operator associated with the atom. So this is a structural prediction of quantum mechanics. It gives us possible values of observables. In addition to the structural prediction, quantum mechanics also makes probabilistic predictions. So it predicts, once you've identified the structure of possible outcomes, it predicts the statistical probabilities of those outcomes based on the preparation you've used. And so the statistical aspect of quantum mechanics wasn't verified till much later. The other thing I wanted to mention is that there's this cute kind of story about Born's rule, which is just to kind of express the sense in which I kind of motivated, well, I did motivate the lectures based on the fact that we don't have a good understanding of quantum mechanics from a mathematical and conceptual point of view, From a mathematical point of view, we have this prescription, which I'm giving you, but that prescription wasn't discovered in a principled way. So many of you probably know that Schroedinger found Schrodinger's equation by essentially playing with differential equations and finding one which met the criteria he knew it had to satisfy. So it was really just toying around with equations and finding one that made sense based on the empirical facts he knew. And secondly, Born's rule, the other crucial ingredient in quantum mechanics, when he submitted the paper for publication proposing how to identify the statistical probabilities of outcomes, he actually suggested that the probabilities were proportional to the coefficients of the wave function expressed in the basis. And then there's a note in proof added in this paper from whatever it was, 1930-something, 1927 or something, 1928. And he says, oh, actually, the correct rule, what's now called Born's rule, is actually in a footnote to the paper. And he says, well, that would give complex probabilities, so actually we have to take the modulus squared of the wave function to get the right answer. So he also was kind of clumsily going along trying to figure out how to make sense of connecting the mathematical formalism to empirical facts. So I just wanted to underscore for you that we have this amazingly successful theory, and it was discovered in a very unprincipled way. So let's connect this to what Born was talking about, which is the squared amplitude of the wave function. So this might be unfamiliar to some of you. Oh, please.
So suppose you only had the structural predictions and not the statistical predictions. What subset of the theory would be preserved if that was all that was confirmed?
That's a very deep question. I think I'd have to think about that more carefully. I don't know if I could. Yeah, if you threw away this assumption, well, so I'll tell you some things that come to my mind which might be related, and you can explore them independently. This recipe is actually implied by Gleason's theorem. So Gleason's theorem says that if I assume some structure of my observables, which might be part of your allowed structure, then the only way you can assign some state, the state then is a mapping from the algebra of observables to empirical probabilities. And one asks, what kinds of mathematical object can satisfy the properties we need for that assignment to work? And he shows that once you assume you have the quantum algebra of observables, this is the unique way to assign probabilities via a state assignment.
I've seen some other things done with decision theory, but suppose you just take the position that probabilities as a whole are just incoherent within the theory that you want to take, and you want to get rid of probabilities. What is left to you?
Yeah, but anyways, I'm not sure what the value of that kind of exercise would be, but certainly it would open up some interesting insights, I'm sure. Yeah.
Various questions. The first one, saying that rho is a projector is limiting us to describe systems by pure states, right?
Mm-hmm.
So
That's what the word ideal is supposed to say. We're not worried about situations where we have less than optimal knowledge.
okay. And the second thing is, shouldn't we infer that rho is the trace of rho is 1, or?
That's a good idea.
Right. I mean.
Yeah. Yeah. If you want your probabilities to sum to 1. Yeah.
Okay.
Yeah.
And the third, if I'm in a finite dimensional Hilbert space, I know what a trace is. Right?
If you're not in a finite dimensional,
If I'm in a finite dimensional.
oh, you know what a trace is. Right.
But in the infinite dimensional case, how do you define the trace?
Okay, that's good. So, sure. Okay, so first, normalization. Normalization is a convention and not a requirement. So that's why I didn't specify it. In that, look, if I want my probabilities to add to 20, I can do that. And I can still do quantum mechanics correctly. So it's just a convention. So yes, traditionally, by convention, we take the trace of rho by convention, I mean, if you study Cox's axioms for probability theory, you realize there's a lot of things about probability theory which are essentially arbitrary, that we just do by convention. So by convention, we take trace rho equal to 1, and this guarantees that, of course, you can't see that until you know the rule for getting probabilities, right? This implies probabilities add to 1. Okay, I remember your third question was how do we define the trace for infinite dimensions? So the trace is a map from, well, a couple of things. So let me not do it that way. Let me just write it down. The trace of some operator B, where B is a linear operator acting on the Hilbert space. Okay, so now let's allow H to be an infinite dimensional Hilbert space. We were promised that our Hilbert spaces were separable, which meant that we have a countable basis. Every basis is countable, which means that we just choose a basis, any basis you want, sum from 1 to infinity, phi L, B, phi L. So this includes, well, sorry, well, I should say D, and then here D is equal to the dimension of H. What guarantees that this sum converges when it's infinite? Hopefully, it's this completeness thing we discussed yesterday, but let's think about it. So,
and phi L are in L2, right?
Where phi L is any orthonormal basis for H, and then because H, if H is L2R, then phi is an element of L2R. By the way, so there's some result, which is that all infinite dimensional separable Hilbert spaces are isomorphic. So remember I gave you two examples of infinite dimensional Hilbert spaces yesterday, square summable sequences and square integral functions, respectively. They're actually isomorphic to each other. So it's just a matter of representation that distinguishes them. So here, phi L is any orthonormal basis for H, which means it's an element of L2R or square summable sequences or whatever. The assumption of convergence, I will have to set aside because it's not obvious to me.
Well, it doesn't. It shouldn't depend on the operating.
Oh, yeah, thank you. Who said that?
It doesn't.
Yeah. Sorry, I missed that. Yeah. Of course, it won't converge in general. I think. Yeah. Precisely. Thank you. Okay, good. So it's not going to be.
I guess if the operator is bounded, that should converge. Right? It's bounded.
Bounded might by this. Bounded by convergence in this context?
Yeah, it's bounded, so it doesn't work. Okay.
Oh, identity is bounded. Okay, interesting.
What about if I take the
Sure.
the nastiest?
Oh, yeah, all the eigenvalues are 1. Sorry?
If I take one of the ugly cases where I take my, I want to have the average value of the position or the momentum, right, which are unbounded operators.
Mm-hmm.
So how can I take a trace in this case?
Well, notice that the average value of the position assumes you have some state that describes your system. So it wouldn't just be the trace of that observable. The trace of that, the trace of Q, position operator, which is unbounded, when the state is identity, which means you have no idea where the particle is, that would be unbounded because you can't evaluate the average in that case. It wouldn't converge. But if you have some state, if you have some Gaussian wave function, which, the Gaussian then tails off at infinity as e to the minus x squared, then you will get something, the average position then will be associated with the mean of that wave packet, things like that. So there's a lot packed in here that, I'm not covering in detail because I want, in the interest of covering more material. But it's good that you're asking these questions so I see which pieces are helpful to emphasize. All right, so I missed your second question, I think. Was there, you asked about the normalization and the boundedness of that trace, and then there was an intermediate question I lost track of. Okay, good, I'm not the only one. It'll come back to you if it's important, right?
What in essence are the conditions that we have, that B has to satisfy for the trace to be convergent?
Well, hold on a second. Why would you want to evaluate the trace of B? I haven't told you that that's something interesting to do. Here, unless B is the product of the preparation with the, remember B, we're taking traces of this multiplication of two operators. We're not taking trace, well, trace just of rho we do take. And trace just of pi doesn't really make sense.
Somehow your projector takes rho into a subset that is finite dimensional, and then you can take the trace.
There's a lot of context. There's a lot of context where we do it. But just in general, just in the mathematical abstract, we don't talk about traces of operators. I mean, that's probably like a PhD thesis on mathematics, right? So let's just talk about what are the operators we want to take traces of for quantum mechanics. And it's these products of preparations with measurement operators. And then in that case, I think I've told you everything you need to know, basically. So if you have a well-formed preparation, a valid self-adjoint operator, and if you normalize a valid non-negative operator, right? Sorry. In general, okay, preparations can be non-negative operators. They don't just have to be rank 1 projectors when you have incomplete information about your preparation. But I'll get to that later. So by the way, I'm going to generalize these axioms for you to accommodate real-world circumstance. This is just the simplest level of idealization. And then we'll see how there are natural generalizations to accommodate experimental realities in a moment. So I don't mean to misguide you there. Did you have a question?
Could you repeat what you were saying about the identity and the bounded properties? Because I didn't follow the discussion.
OK, so when you go to infinite dimensions, there are a number of mathematical subtleties that arise pertaining to unbounded operators. And so how does one evaluate this trace given some operator B? The trace in general is defined as sum over an orthonormal basis of these expectation values of B. It ends up being, when B is self-adjoint, this ends up being equivalent to just adding up the eigenvalues of B. Now, if B is unbounded and has eigenvalues that go from minus infinity to plus infinity, then it's not a well-defined object, what it means to sum over the numbers minus infinity to infinity. And you could say it's 0 by fiat or something, but it's just not well-defined. And so that was the issue we were discussing, was what does it mean to evaluate this trace? When does it converge? Well, it doesn't always converge. And the point is, when we're taking the trace of a self-adjoint operator that's unbounded, and we're getting something that doesn't converge, what that tells us is that's not a well-formed question in quantum mechanics. This doesn't correspond to something empirical. You guys know what I mean by empirical, right? It doesn't correspond to something observational, observable, because it gives us something that's undefined mathematically. And I was saying, look, the only objects you end up getting, quantum mechanics only claims that under the stipulations I've given you, that this object will be well-defined. It will give us a probability. And here we restrict rho to be a rank 1 projector, and we restrict pi to be also a projector in the spectral decomposition of A. So under those conditions, this will give us a well-formed probability. And there are a whole bunch of subtleties in dealing with position and momentum, because those are unbound operators. So essentially, the eigenstates of position and momentum operators aren't, the eigenstates of those operators are not elements of the Hilbert space, as I mentioned earlier. And that's part of the problem there. But there's ways to accommodate that, which we'll discuss, and they're not fun. OK, so, well, I mean, I guess they're fun for some people, people that like these mathematical subtleties. OK, maybe before talking about dynamics, I'll switch to a canonical example to kind of make some of these abstract statements more concrete. Oh, I had promised you to connect this form of Born's rule. I might be biting off more than I can chew since I haven't covered some things I need yet. But how do you relate that to the usual rule? Normally, you're told, OK, well, the probability of x, so here's a compare. The probability of x is equal to psi x squared. This is how Born published his rule in the footnote. The original statement was probability of x is equal to psi of x. And then he realized that wasn't well formed, and so he changed it to this. So we can't quite without discussing self-adjoint operators, unbounded self-adjoint operators, I can't make this more precise. But what I can do is I can consider H equals C2. So this is a qubit, a two-level system. So I would have, let me just define an orthonormal basis as 0 and 1. All right, then psi is equal to alpha 0 plus beta 1. Our preparation rho is associated with psi psi. This is a rank 1 projector. Oh, yeah. What's the trace of a rank 1 projector? Right. So my convention is implied by my axiom. All right, so rank 1 projector. And then now notice this is slightly more general than we need. We know that the overall phase of psi is physically irrelevant. We know that because of the Born rule. So let me just show you the Born rule in my approach. We assume A is some observable, and let's let it have a spectral decomposition. A minus plus A plus, where plus minus is some orthonormal basis for our Hilbert space that's not the same basis as 0 and 1. Then we say the probability of outcome minus is equal to the trace of rho against minus minus. Okay, so this is just confuses some people, so let me tell you. Normally you would write the projector onto the state minus like this. Okay, it's easier just to make this an x. Okay, so it's a little bit sloppy, but that just means bracket back to back, okay? So now we get the trace of psi psi against minus minus. Which is equal to psi minus squared. All right, so we recover, remember psi of x is, and psi of x is, loosely speaking, equal to x psi all squared. But remember, this is, I mean, you did this in undergrad, but here, remember that the ket x is not an element of the Hilbert space. Okay, so that's the cheat you were all taught that now you're going to unlearn. Okay, so this is not a Hilbert space vector. And so we recover what looks like Born's rule from our approach. But this formulation is going to allow us to talk about preparations that aren't pure states. And it's going to allow us to talk about measurements that aren't given by self-adjoint operators, which are important generalizations to accommodate what happens in the real world as opposed to the ideal prescription of quantum mechanics. Okay, so that's a mathematical picture. Now let me give you a physical example. We'll talk about Stern-Gerlach measurement. Okay, so now we have our measurement, our preparation box spits out this invisible thing, which we'll assign a preparation rho to. And then we'll just skip the transformation box, and we'll go right to the measurement box. So here's my go button. And here's my light bulb. And here's my pointer. Here's my knob. Here's this knob. Okay, so I turn this knob, and I get various choices of preparation. I'm going to choose the preparation rho, which is equal to, here, let's change variables for fun. Let's call it phi. Actually, you know what? Let me just call it psi, and we'll just use the same notation as there. This is psi. So here, psi is alpha 0 plus beta 1 as before. And then my measurement, what does the Stern-Gerlach measurement do? What's going on inside this box? Okay, so now let's look inside the box. And what we find is that you have a magnet like this. So let's suppose that this is a spin-half particle. And then this is a magnet where one of these is north and one is south. The spin-half particle comes out of this box, goes into this one. This is inside of our box here. And here's our light. And then the particle is going to come in, and it's going to get a deflection, a momentum kick up or down, depending on the spin. So it's either going to get deflected up or down. And then what we do is we have a wire chamber detector. A wire chamber detector is basically, so let's imagine this is a charged particle. So this would not work for a neutron. So a wire chamber detector works like this. I built one of these for my master's degree before I quit experimental physics. When you spend a year polishing aluminum for a good vacuum seal, it makes you reconsider your career options. All right, so then the particle gets deflected upwards. It's a charged particle. Now the point is, the function of this is that, remember, you have a coupling, you have an interaction coupling, which is basically the spin magnetic moment couples to the gradient of the magnetic field. And therefore, you get essentially a momentum kick up or down depending on the spin degree of freedom. And so what happens is then if we have spin up, if we send in just the spin up state, it'll get deflected upwards, say. I mean, there may be some sign here I can't remember, so let's just assume that's the case. It goes upwards, and then the spin of the particle is upwards, and then the particle goes through this chamber. So what this chamber does is it has a gas in it. And what happens is when the charged particle goes through the gas, it ionizes the gas. All right, that's a very natural thing to happen. And then when the gas gets ionized, what we've done in advance is we put a positive charge on these wires and a negative charge on these wires, on this end of the wires. So now when the gas molecules get ionized right here, that creates a small voltage, a small current on this wire, which is then pushed here, and then we have electronics that couples to our pointer, and the electronics pushes the pointer, say, left. We'll call this up, and we'll call this down. So the electronics feeds in here. We have to set the light off because we saw a signal, and then we push the needle this way with our electronics. I won't draw what's happening inside the electronics box. Same thing down here. If the particle goes through the lower chamber, we get an ionization of the gas, which leads to a current on the wire, which then feeds into our detector apparatus, sets the light off, and pushes the arrow right for down. Okay? So now what we've done is we've managed to detect whether the particle had spin up or spin down. And this dashed line is what's happening inside this box. Okay, so now the interesting thing when we get into questions of measurement is that Born's rule is just telling us what's the probability of getting a signal in this wire chamber. Well, that probability of up is equal to the trace of psi against the up eigenstate. And similarly for down. And this ends up just being, let's call 0 up, and let's call 1 down. Normally this would be plus a half and minus a half, but these are just labels. Then you find that this probability is equal to alpha squared. And then when we talk about the theory of measurement, we'll discuss all these interesting things like, what is the state after the measurement? Why is it that when we're in a superposition of up and down, we only get one detector click, either up or down? How do we resolve those questions mathematically and conceptually? So we'll discuss that in depth. Those are very subtle issues. Okay, good. Any questions about this description? Or was that too basic for you guys? You look kind of bored. Okay. All right, good. So what's next? Questions or some mathematical details about measurement? I think I've covered everything for measurement. All right, so let's jump right into transformations.
haven't said anything about the post-measurement state.
Yeah, I'm not telling you that yet. That's to be discussed. That's an interesting topic, though, so I'm excited to get to it, but patience. Let's at least finish the axioms. All right. Axiom 3. Ideal transformations are generated by a linear operator U such that psi at time t2 is equal to U t2 comma t1 psi at t1 satisfying I h bar Okay, so this is Schrodinger's equation expressed in terms of the unitary operator. There's a little bit more where H let me call these dynamical transformations, where the word dynamical is meant to denote transformations in time, where H of t is the energy observable t is time well, I should just call it the energy function, whatever. T is time. And what else am I missing? Oh, an initial condition. We have the initial condition that U at T1, T1 is equal to the identity operator. Yeah.
Is there a reason you're calling it the energy observable as opposed to the Hamiltonian, since those two things are not always the same?
Is that right? They're not the same. I mean the energy, I mean the Hamiltonian. So I can just write that, but what do you have in mind?
Well, for time dependence.
Oh, yeah.
I think you have magnetic.
Yeah. Well, I guess there's some ambiguity there. So right, let's just call it the Hamiltonian.
Can you repeat that, Joe?
Okay, so the question was, instead of energy observable, do I mean Hamiltonian? Because in the context of time-dependent systems, the notion of energy and Hamiltonian might not be the same.
I think there are situations that we can have Hamiltonian.
So I'm not, off the top of my head, I don't recall those situations, but I have no problem calling it the Hamiltonian. Okay, so we're done with the axioms, all right? But there's a whole bunch we've left out. So I have some quantum system. I want to describe its evolution. What is the Hamiltonian? How do I find out what the Hamiltonian is? I have some device that prepares a system. How do I assign a particular choice of operator to describe that preparation? there are a whole bunch of auxiliary axioms we need in order to use quantum mechanics. But here what I'm trying to do is just lay down the axioms needed for giving a mathematical characterization of quantum mechanical systems. So it's analogous to classical mechanics. I mean, you learn about Hamilton's equations of motion as the dynamical laws of quantum mechanics, but it doesn't tell you how to find the energy function associated with some interacting system of particles. So in a sense, quantum mechanics is describing kinematics and dynamics, but telling us nothing about the physics, right? So quantum mechanics would still work and still describe systems if we lived in a world where the Coulomb interaction was not 1 over r squared. Those kinds of properties, assigning Hamiltonians to describe physical interactions, is logically independent from the quantum formalism for describing dynamics and kinematics. But to actually use quantum mechanics, we need both laws of physics, like electromagnetism and gravity, in addition to these axioms. All right? So bear that in mind. I'm also not putting the description of how the state, what is the state after measurement, as an axiom. And I'm not entirely sure that that's the best thing to do. But the point is, remember that the state after measurement is just another way of preparing the system. And I've already told you that for every preparation, there exists some state operator, some density operator, which will describe that preparation. What that density operator is a question we have to answer. And so we'll address that. It could be elevated to an axiom, but I'm kind of back and forth on that issue. And the other thing we haven't talked about yet is composite systems, the tensor product rule for combining systems quantum mechanically. How does that come out? And so there's a way to suggest that that's implied by the structure of the observables, which I'll discuss in a moment. So tentatively, let's say these are all the axioms we need. Let me elaborate a bit on axiom 3. Do you have a question you wanted to? Good.
So you said what you mean by ideal for axiom 1 just meant the pure state. So if it's non-ideal, you need some non-ideal unitary operator, non-unitary operator with the pure and the coordinate state.
That's exactly right. So decoherence is a mechanism that's physical and ubiquitous. And in general, in the lab, you'll see that your transformation was not unitary. It was something called a completely positive map, which is what happens when you have a unitary transformation on your system and environment, and then you ignore the environment degrees of freedom. You're left with an effective transformation, which is more general than a unitary transformation. And that's very much consistent with quantum mechanics, but it's in a context where you're ignoring, it's a question of what do you call system, right? So if your system is the whole universe, then by hypothesis, the transformation is unitary. If you're looking at a subsystem, then you're not guaranteed the transformation will be unitary because of the fact that electromagnetism drops off as 1 over r squared, so you can never really shield your system perfectly from other systems. Okay, let's talk a bit more about axiom 3. So I haven't said that U is unitary. It's actually implied by this. Okay, so let's see that first. So, well, okay, I didn't show this in my notes, but I've done this at various points in my life. But basically, this implies that U is unitary. Okay, so how do you check this? So a linear operator U is unitary if U dagger is equal to U dagger, U is equal to identity. So it's a matter of essentially take the adjoint of this differential equation. This would be a good problem for the students to work out in the tutorial. Take the adjoint of this equation. So if you take the adjoint of the whole left-hand side, I becomes minus I, U goes to U dagger. If you take the adjoint of the right-hand side, remember you change the order of the operators and then apply the dagger to each one. Okay? And then you get an expression for U dagger and U. You use the initial condition, and you can prove that the only unitary that satisfies this equation is one that's unitary. The only linear operator satisfying this equation, so unitarity is implied. Okay, and I'll leave that as an exercise. Yes, yes, yes. Okay, in the time-dependent case, so if H is time-dependent, then the general solution to our axiomatic equation of motion is given by U of T2, T1 is equal to the time-ordered exponential Okay, so the reason for the time ordering here, something I'd like to assume you all know, but basically let me just repeat it just in case. Suppose I have a Hamiltonian which for the first times 0 to tau is sigma x, and then from tau to 2 tau is sigma y. So my Hamiltonian changes. This is physically very relevant if you turn on and off some magnetic fields that are affecting your system at some time. Then the evolution is described by some Hamiltonian for some amount of time tau and a different Hamiltonian for another timescale tau, and those two do not commute. That's the key point. So in that example I gave, you would have the time ordering tells you from 2 tau to 0 is equal to, first, what happens on the right-hand side is exponent minus I sigma x. Let's give it some constant b. This is the strength of our magnetic field along the x-axis over h bar, and this happens for a time tau. And then after that, so we go from right to left. Remember, U acts on the state from right to left, so the rightmost term happens first, and then the leftmost term happens second. And then here we'll have minus I sigma z bz. Sorry, I didn't leave myself enough room. Tau divided by h bar. Okay, so our time dependent, the time ordering means that I put the Hamiltonian that's happening first on the right, and then I evolve under that, and then second, the Hamiltonian that happens second. So this is valid if bx is not equal to 0 for 0 to tau, and bz is not equal to 0 from tau to 2 tau. Yes?
You separated in both exponentials, right? That's why. I mean, I have the exponential of the two Hamiltonians, right? I mean, my h of t is a function that depends on time.
Yeah.
Right? You're saying that both of the Hamiltonians do not commute.
Mm-hmm.
Okay. So this is just a formal expression of what u is, right? But then what I'm saying here is that you're implying that the exponential of the two terms is the product of the exponential of each term?
Yeah.
And that's because of the time ordering.
That's
Even
because of
though
the time
both
ordering.
the operators do not
So yeah, sorry. I mean, in generally, what you can have is you can have more complicated. This is a simple example,
Okay,
just to explain time ordering. So in general, you can have h a continuous function of time, and then at every instant, h does not commute with itself. And then you have a more complicated problem to describe mathematically, which you would probably do numerically or something.
But I mean, my confusion is the following. I'm between T1 and T2, right? So if each of T is piecewise continuous, then I divide integral into two integrals, right? As the sum of two integrals.
Oh, I see. So you're saying this is a piecewise continuous function, and you're saying, so why isn't it just the sum rather than the product?
Why is it not the exponential of the sum
Yeah.
of the terms instead of the...
Yeah, yeah, okay. Well, that's what the time ordering is telling you. You're not allowed to do that, right? If I didn't write this there, you're exactly right. You would tend to just write everything inside the argument, and you would have e to the I A plus B. But that's not physically correct, right? So A is, one of these terms, and B is the other one. Okay. So in general, for non-commuting operators, this is not true, and this is what we want physically to describe what's happening, and so we put this symbol here to remind us of that. Thank you for that question. Now, of course, if H is time independent, or if it's time dependent and the terms commute with each other, we get a simpler description. So let's look at a time independent case. Let H be time independent. Then we have, in general, U is equal to, well, I should write U of t, is equal to exponent minus I ht over h bar. And then here's the key point, is that then I can take this equation and I can differentiate this equation. So I'm going to take d psi by dt2. And I'm going to be dividing by dt2. I'm going to be differentiating with respect to t2. So now I have to differentiate u with respect to t2. And this doesn't depend on t2, so that's all I have to do. And then what I do is I say, okay, well, I know what du by dt2 is equal to. It's equal to hu divided by h bar. So I can substitute that in here. And what do I get? What I get is axiom 3 implies that I h bar d psi by d2 is equal to h of t2 acting on psi at time t2. Okay, so that's the usual form of Schrodinger's equation, which is implied by the way we formulated our axiom. Okay, so this is the Schrodinger picture. What I gave you here is the Schrodinger picture where the state evolves in time. And you should certainly all know the difference between the Schrodinger and the Heisenberg pictures. Let me just recap, recall. Once we have our unitary is our primitive. Given U, we can take the Schrodinger picture in which, psi of t is equal to u of t acting on psi at time 0. And I'm taking the liberty of calling t1 0 and t2 t. And we have the Heisenberg picture in which we let the observables evolve in time. AH of t is equal to u dagger of t, AH of 0, u of t. And then the point is, either way, we get the same physical predictions, right? So in the Heisenberg picture, we have the trace, the probability of outcome k is equal to the trace of before I do that, there's something I wanted to mention, which is an important conceptual point. So this is a digression. I excuse the misordering of the material. I should have mentioned this earlier. Okay, so what you learn in undergrad quantum mechanics is that quantum mechanics predicts things like the expectation of A, right? And this is given by psi A psi. And these are the kinds of things you calculate when you do problems. This is not a good way to think about quantum mechanics, okay? Because it's very misleading conceptually. So essentially, what the best way to think about quantum mechanics is in terms of the spectral decomposition of the observable. I called this index K before, but it's just an index, so let's not worry about that. And then you realize that the expectation of A corresponds to the sum over L, AL, psi, pi L, psi. Which means that the expectation of A is equal to a sum over L, AL, the probability of outcome L, via Born's rule, as stated in my axioms. So now what's going on here? What you realize is that the experimental primitives, these are the experimental primitives. The probabilities of each of the allowed outcomes. And then when I talk about the expectation of A, I'm throwing information away. Okay, so when you calculate the expectation of A, you're not giving me the best information I can get. What I really want to know is these probabilities. Because you can have a whole bunch of expectations of A that are consistent with different probabilities of outcomes. So I'm under-specifying my observable outcomes when I talk about this. The point is, the probability of each outcome L against L, the different eigenvalues of my observable, is going to be some histogram like this. Okay, so I have different probabilities for each outcome L. Let's start. Well, I don't have to start from 0. Now the expectation of A says the following. Let me take the probabilities of each outcome. Let me weight them by the eigenvalues. So this is just a weighting factor. And then report the average. So the expectation of A is just an average over experimental realizations. Well, the probability is also kind of an average over experimental realizations. But the point is that I can have two very different probability distributions corresponding to different preparations, which give me the same expectation of A, right? So the point is that there's many probabilities giving the same A. So from a fundamental point of view, what I care about the most is this. I record that data, and then this is just something I do after the fact. It's a post-processing. I'm going to start, I'm going to say, well, I want to give this probability, this weighting, and so on. Notice that if I record this information, then I can also calculate A squared is just the sum over L, AL squared probability of L. So it's the same input data, and I can calculate a different observable after the fact. So the same experimental arrangement, the experimental arrangement that gives me these probabilities, I can then use later to calculate a whole bunch of different functions, including something like B. If B commutes with A, then I can also calculate it where B is equal to a sum over L BL, and then let me make the projectors the same. What do I call them? Pi L. So I have an observable with the same eigenspaces as A, but different eigenvalues. And I can compute its expectation from this data just as well as the expectation of A. Okay, so the focus, really what one should focus on are these probabilities rather than the averages. So really here the expectation is really the average over my outcomes with a weighting prescribed by the eigenvalues. So now once I've said that, then the Heisenberg picture, the point is we should focus on cases where the observable A is a projector, right? That's the most fundamental we can get. And then when the observable A is a projector, let AH of t equal P pi L, and this is Heisenberg picture of t. Then my probability of outcome L is equal to the trace of rho at time 0 u dagger pi L u. And then I can use the cyclic property of the trace to take this u and bring it over here. And then I have u rho at time 0 u dagger pi L. And then I can talk about this piece here being time evolution in the Schroedinger picture. And I just get the trace of rho of t pi L. So in other words, whether I work in the Heisenberg picture where I have time-dependent observables, which are where the time evolution is, where the dynamical time evolution is ascribed to the observables, and I sandwich the observable and evolve it in time between these unitaries, or whether I evolve the state, it's the same. It gives me the same predictions. So we have a freedom in how we think about quantum mechanics. And that freedom is given by the Heisenberg versus the Schroedinger pictures. For calculational purposes, there's another picture that's useful, which is called the interaction picture. And there, typically, if you have a part of your Hamiltonian that you like and part of it that you don't like, so part of your Hamiltonian is your self-Hamiltonian and a part is some interaction that's maybe hard to analyze, then what you want to do is you can evolve your state under the easy part of the Hamiltonian and your observable under the hard part of the Hamiltonian, and that buys you some calculational advantages in perturbation theory. So that's something you should also be aware of, but I may or may not discuss later. Yeah?
Related to that, you're assuming that you can evolve with the free Hamiltonian and the other Hamiltonian independently, even if both Hamiltonians might not commute?
Yeah, okay. I don't know about what independently means there, but the point is you evolve part of your system in one frame and part of it in another frame. And
which is kind of saying that you separate into two parts. I mean, it's the product of two U's.
Yeah, you end up making, well, it's a perturbative approach. So what that means is it's not going to give you exact answers. It gives you approximate answers. So it works when the interaction is weak compared to the self-Hamiltonian. And then it turns out if A or B are in some sense small, then you can make this an approximation. And then the correction term is the commutator of A and B. And then in the interaction picture, you get the commutator of A and B comes into play. And then you can do some approximate calculations using that trick. So I just wanted to give you a heads up about that. Yeah?
I'm a little confused about that statement. In that first line, you have that pi of L in between the unitary. Is that pi of L at time t, at time 0?
Yeah, so this is pi of L, it's like your position operator. It's just the position operator.
At what time?
Anything.
At any time, really.
Your Heisenberg picture works for any time.
So the problem I'm having is when you use the cyclic property of the trace and bring it over,
Mm-hmm.
and you're acting with you're taking the role of anything back.
No. So the point is this: forwards in time. When you're applying time evolution to a state, forwards in time means u rho u dagger. In the Heisenberg picture, forwards in time means u dagger a u. So you have to change that's the only thing you have to remember, basically. And now, this is easy because I've assumed that my observables are intrinsically time independent. So I've assumed I have something like I'm measuring sigma x. Okay, so sigma x is my observable. This actually gets really, I wouldn't say subtle, but it's non-trivial when you have time-dependent observables. What goes on there, suppose I'm measuring sigma x of my spin particle. My spin's evolving into some Hamiltonian. Suppose that I have an experimental apparatus which involves some rotating magnetic field. So what I'm calling sigma x is actually changing in time with respect to my lab frame. Okay, so then I have a time-dependent observable. But my state is also evolving from some Hamiltonian interaction with that, maybe with that field and other fields. So then what happens is you have two kinds of time development. You have the time development due to Schrodinger's equation, and you have the time development due to this extrinsic or intrinsic, I forget which word is appropriate, due to this intrinsic time dependence that you've built into your apparatus. Then you have to be good at accounting at that point, okay? Because you have to keep track of these various effects. And with probability 1, when I describe this in lectures, I get it wrong. So I prepared some sheet to make sure I always got it right. And I don't have that sheet with me, so I'm not going to do it. But I can provide that to you as a handout. And so it's just really important to make sure you understand those nuances of which time dependence is at play. And it's really just a practical issue that arises that you have to account for. So Aggie, will you remind me to get that sheet because I'll forget. Okay, good. The next topic is composite systems, tensor product structure, which is kind of the underpinning of entanglement and all these other interesting properties when you have more than one system at play. I don't think I have time to launch into it, so we'll do that tomorrow. Thanks for your questions.